Swayam Prabha. Digital India. Educated India.
In this last module, which is 7th for this semester, we will be trying to become ambitious for covering the entire space of dispersed systems in just about 40 minutes. And the topics I intend to touch upon are outlined there: colloids, aerosols, emulsions, foams, coagulation, and one of the most important theories for coagulation, Smoluchowski's theory. I did mention a bit about dispersed systems in one of the earlier lectures. However, we haven't had a chance to look into how the dispersed systems owe their thermodynamic nature, how partly the intrinsic thermodynamic nature could be modified, and in those systems where the effect of interfacial energy is too overwhelming, how we could analyze the breakdown of dispersed systems. That is what we will try to look into today. Let me begin with the slides. We might interchange with the visualizer. First, some generic remarks about dispersed systems. First point to note here is that the dispersed systems are thermodynamically unstable. Why does this happen? As the name suggests, we have one of the phases dispersed in another, perhaps at very small dimensions. And if we have particles or droplets present within the continuous phase of the dispersed phase, we expect the interfacial energy to be very high. That is the genesis of the unstable nature of the system, the very high interfacial energy associated with the large interfacial area in these dispersed systems. And it is a thermodynamic tendency for a system with high interfacial energy to respond to lower that high energy, and that could be done by spontaneous coagulation or coalescence or aggregation of these droplets or particles, forming larger clumps or coalesced droplets, which then will have lesser specific interfacial energy. And that is one way the system could respond to the unstable nature. So, it is the interfacial free energy which is large and positive, which leads to this kind of behavior, and we call such systems as lyophobic dispersions. By that we mean that the droplets would aggregate or coalesce rather than remain in contact with the continuous phase or solvent. So, it is the tendency to coalesce or aggregate and minimize the contact with the continuous phase or the solvent phase. We did refer to colloids very early on when we talked about fluid bounded persistent structures, submicroscopically small in at least one dimension. And here we come to that dimension. We will call a dispersed system as a colloidal solution if that one dimension is less than about 10 raised to minus 7 centimeters to 10 raised to minus 4 centimeters. If the particles are smaller than this range, we will call them colloidal. Next question will arise as to how these lyophobic colloids can be prepared. There are two classes of making these colloidal dispersions or solutions. First, we have the class of methods which are the dispersion, which refer to one of the phases being torn in another phase, making smaller and smaller fragments of this particular phase, which will end up as a dispersed phase. The other one is condensation. As you are familiar with condensation, it would involve supersaturation of a phase with a solute. As a result of this supersaturation, we will have precipitation into very small particles or droplets, leading to the colloidal dispersion by the condensation method. It is here that it might be worthwhile to know that in condensation, which is akin to crystallization, the supersaturation can itself lead to two different ways of forming these submicroscopically small particles. One could think of nucleation here. We may have ultra high supersaturations leading to spontaneous formation of molecular clusters, which are few thousands or few tens of thousands of molecules forming aggregates as a result of thermodynamic fluctuation. Such kind of clusters would always form when we have very high supersaturation. What fate do these clusters or nuclei suffer? There are two possibilities. Just a similar kind of fluctuation which has brought these large number of molecules together forming the nucleus. Subsequent fluctuation could take them apart. So, we might have this dynamic formation and disintegration of nuclei. However, when you do the analysis based on total energy for such clusters, it turns out that there is a critical radius of a cluster below which these clusters will be necessarily unstable. They may form, but by the similar fluctuation as is creating those nuclei or subnuclei size particles, those will disintegrate also. But if the particles have, these nuclei have critical size or higher, then they will grow into larger particles, droplets, crystals, whatever we have.
There are two contradicting energies, the surface and Gibbs.
Right. So, we have the surface energy, and then we have the volumetric, the bulk term corresponding to energy. So, when we take these together, it is possible to show that there is a critical size of nucleus below which the clusters would be unstable. This is purely talking about supersaturation and generally very high supersaturation driven nuclei formation or nucleation. But most realistic systems, as you would anticipate, won't be so pure, there would always be some kind of sites for nucleation, very fine dust particles for example. Those fine heterogeneities could be the preferred site for condensation or precipitation of the solute which is coming from this supersaturated surrounding solution. So, if we have those extraneous particles serving as a shortcut to nucleation, we have heterogeneous nucleation, as opposed to very clean systems where the nuclei will have to exceed the critical size and that will require very high supersaturations. The heterogeneous nucleation is relatively easier at lesser supersaturation driving force. We will have the condensation bringing about formation of these colloidal particles. That is precisely the reason why when it comes to the precipitation leading to rain, we have the role for dust particles, or in artificial rain we seed the clouds with nuclei, silver iodide particles for example, or in crystallization you have the seed crystals added which serve as sites for nucleation. In any case, this is the other method where the supersaturation driven formation of colloidal suspensions or particles solutions could occur. The lyophobic colloids with concentrations of particles in excess of about 10 to the power 10 per cc would tend to coagulate rapidly. The particles see each other, they collide, and if they have very high surface energy, this is one sure way of removing that unstable character. Particles could come together, join together, so that the effective area goes down, the energy goes down. So, it is here that you can think that lyophobic colloids with very high surface energy for particles would tend to have every collision fruitful. Every collision results into clumping together or aggregation of particles. This is how the colloids would break down, but having said that, yeah.
Confusion between condensation and supersaturation both, as in
Okay.
suppose where there is aerosol droplets of very small size and the cloud the cloud droplet, the water vapor gets stuck to it. So it's a super saturation, or what is it?
No, I said there are two ways in which you can have the colloidal particles forming in condensation itself. In condensation, you could have one kind of system which is relatively rare, very pure system. There is only the supersaturated solution. It could be the water vapor in air free of dust particles, okay, or it could be supersaturated solution in a crystallization system without any seed crystals or roughness on the surface, because those particles, if they are present, they are sites of lower free energy. So, the system goes by relieving the supersaturation by depositing this solute, which may be the vapor or the solute in the supersaturated mother liquor. It is now deposited onto these particles. No? So, if the particles are present, it is a heterogeneous nucleation. If there are no extraneous particles, dust particles or roughness on the surface or seed crystals, then we have only the solvent and the solute. And if such a system has to form nuclei spontaneously in these very clean systems, you need very high supersaturation. In crystallization literature, you would come across supersaturation to the tune of say about 1500% over saturation. You require that high supersaturations in order to have any crystal nuclei forming, okay? And that is homogeneous nucleation. So, homogeneous nucleation is in a very clean system, heterogeneous nucleation where there are some seed nucleosides to build up the nuclei, right. Now, we are returning to something which is colloidal particles which have very high energy. We might only have the colloidal particles of the dispersed phase and the continuous phase, and these particles, they are moving about. They may be large compared to, let us say, molecular dimensions or the molecular free path, but they are still not so large as to be in relatively static positions. Now, what I am referring to is probably the dimensions of particles which might exhibit Brownian kind of movement. The zigzag motion, which is the result of non-equilibrium conditions in the continuous phase. The particles are small enough to be able to show the non-equilibrium effects, but they are large compared to molecular dimensions or mean free paths. Now, it may take a different level of understanding this. If such particles are there, they are moving about. It is interesting that the hypothesis that such particles, such small particles capable of displaying Brownian movement might exhibit a property similar to what we see in diffusion. How these particles move from one region to another might show a similarity with diffusion. Obviously, we are not dealing with molecular system, but much larger particles. So, the characteristic transport coefficient is the Brownian diffusion coefficient. We will see later how to predict or estimate that Brownian diffusion coefficient given the size of particles. So, you can visualize on one hand the kinetic molecular theory for molecules. Molecules are getting bombarded by other molecules, they move about in random chaotic fashion, and on the other hand you have these colloidal particles much larger than molecular dimensions or mean free paths, but they are also slightly more sluggishly, but moving randomly and chaotically, and the two have a certain analogy which is of diffusional character. Okay. So, these particles which are moving around, if they happen to collide against each other, they will tend to stick to each other, thereby they will lower the energy. We might otherwise say that these particles or droplets which are getting bombarded against each other, they get adhered to each other. You might have adhesion of these particles. The moment they come together, they clump together. And the chances of such a thing happening are obviously high if the particle concentrations are large. So, that is why this number was there. If we have number of particles per cc in excess of 10 to the power 10, we might have such frequent collisions leading to the clumping or agglomeration or aggregation of particles. Now, for such a system which is called as rapidly coagulating system, a certain theory was advanced by Smoluchowski in 1916 to be able to estimate how the number of particles in the system would change with time. And it turns out that that simple theory is in pretty good agreement with experiment. We will shortly see what that theory is. I will try to simplify the picture as much as possible, but we can alongside look at the more rigorous derivation also. Before we do that, let us think of the practical part of it. If we have such rapid coagulation systems, in practice you may not always want. After all, the dispersions may have to be processed over certain lengths of time. You might not want these dispersions to break down very quickly, and many products will require the dispersions to be metastable, as stable as you can practically have. So, often we need this stabilization that could be done either through electrical factors or through solvation barrier. electrical factors you can imagine if, let us say, the colloidal particles carry surface charge. Typically very small droplets or particles may carry negative charges, and if they are suspended in the medium, then it means that even though particles come very close to each other, the electrostatic charges would repel them. So, that is a stabilizing factor. If you want to destabilize, you should be aiming at removing that charge, or alternatively we might have solvation barriers. We might deliberately coat these particles or droplets with amphiphilic molecules like surfactants, and therefore, there is a barrier, the energy is lowered, and if the particles have to bring the native surfaces together, they will have to rip off these surrounding surfactant layers, which will not be easy. So, there are those kind of barriers possible. So, through such expedients, it is possible to stabilize dispersions even when the concentrations are in excess of about 10 to the power 14 particles per cc. So, we can make such dispersions, colloidal dispersions, last for long periods. If we achieve such stabilization, it means now very few of the collisions will be fruitful or effective in reducing the energy, whatever residual energy in the surface is, and that will amount to something like 1 in 10 to the power 6 collisions, or 1 in about 10 raised to 8 collisions might actually succeed in coagulation. So, it is possible to tailor make the stabilizing factor such that you reduce the coagulation frequency or efficiency by a very significant factor, and such very stable dispersions are quite common in practice. Some of the dispersions could be made stable for up to several years. Having said that, and having earlier mentioned that the mists or smogs, aerosols, could be made harder to disperse if tarry material is present, we can't actually stabilize mist or smoke that much. Foams, on the other hand, can be stabilized, as I mentioned earlier, by having factors like these electrostatic repulsions, and you can preserve soap films for several years. Yeah.
If smokes are not stabilized, does that mean they will always get coagulated?
Yeah, they will coagulate. You might be able to delay it a bit, but not so much. You can't make.
What is the limit of the coagulation?
You just have to look at what is the time it takes for the smog to last, even in the most polluted cities, of the order of few hours at the most. We can't, however, use this Smoluchowski's theory for coagulation of foam, because we have very high volume fraction of gas. In typical foam, you may have 97% or higher percentage of volume of gas dispersed in liquid. In those systems, the stability depends on other factors, the drainage of liquid or thinning of foam films, and other mechanical factor. And often it is required to break the colloidal dispersions. It will help here how the colloids are stabilized. Once we know what is the stabilizing factor, we can take countermeasures against the stabilizing factors. If it is the charge, you might think of neutralizing the charge by introducing, let us say, in a negative charge stabilized colloidal system, you can introduce maybe cationic surfactants, where the adsorbing component will carry positive charge. So, it will annihilate the negative charges. Once the particles become neutral, then it may be easier to break down those kind of suspensions or emulsions. So, in the remaining time, let us focus on the collision rates in dispersed systems or Smoluchowski's theory. It is here that I would like you to think of the system as having all initial population of particles, which we will call primary particles. Primary particles are the particles that we start with. For simplicity, we may say all those particles that we have in the beginning are of the same size. It is possible to build up more rigorous versions of this theory, allowing for the polydispersity of particles, but let us say to get the key concepts and approach right, we think of all particles to be of same size, and they are moving around with some characteristic transport coefficient, the diffusion coefficient d, like the Brownian diffusion coefficient, with the same units as of diffusion coefficient, molecular diffusion coefficient. This will relate the flux of the particles to their gradient through this Brownian diffusion coefficient. We may think of the primary particles number concentration as being represented by the symbol n subscript 1. N1 is the number of primary particles per cc, and there will come one other parameter called collision radius of particles, capital R, or what is stated originally by Smoluchowski, the radius of sphere of coagulation. I need to explain this a bit. Let us say you have certain primary particles. We have these particles of same size, all moving around randomly, and over a period of time we will have reduction in their number and so on. If the number of primary particles per volume is n1, that will be function of time, and we might be interested in how this total number of particles within a system is changing with time. Now, in Smoluchowski's theory, what is visualized is the following. Smoluchowski hypothesized the following approach, that you can take any one of the particles, primary particles, and regard it as stationary, and around this particle he said there is a sphere of coagulation or sphere of influence with radius which is capital R. Now, that is a hypothetical envelope around the particle. He says if any other particle crosses this sphere of coagulation, it will get bonded to this particular particle under reference. So, you can now think that in this population you have one particle arbitrarily chosen to be stationary, and around that there is a whole population of these other primary particles. They are all moving about. Around this arbitrarily chosen particle, we have a certain sphere of influence or coagulation, such that any other particle which crosses the boundary of this sphere will get bonded to this. In other words, in this case it is simple, another particle will cross this when their centers differ by the sum of their radii. The particles touch each other, right? Every contact between particles is fruitful, leading to aggregation. So, this sphere of coagulation is a concept. Around the sphere of coagulation till infinity you have all the particles. If this sphere is acting as something which is able to make particles vanish, we could say the number concentration of particles at this boundary will be always 0. Anything which comes to that point will get immediately removed from the system. So, the free primary particles number concentration on this spherical envelope will be 0. Far away it will be whatever is initial concentration. Supposing initial concentration is N0, that will be the N10, that is the initial concentration far away. Here the concentration is 0. Now, you have two ways of looking at it. Rigorously speaking, you take the spherical coordinates and find out what is the profile of concentration which makes it vary from N10 at infinity, at the radial coordinate of infinity, to 0 at this sphere radius or at r. Then you can actually find out what that concentration profile is. You can try calculate the flux and then you multiply that flux by the area of the sphere and get the flux. That will give you a measure of what will be the collisional frequency of like particles, primary particles. And then we should be able to relate it to how the total number is changing with time. Or maybe even simpler, and I will just seed this idea. You could take the film theoretic picture. You can think around this sphere a film across which there is a steady state kind of transport, and you are using a pseudo steady state kind of approximation. The flux is given by the film theoretic picture, and again the total area of the sphere times that flux will give you the rate of disappearance of particles, primary particles. All right. So, based on these approaches we could consider the equations here. So, let us look at this. Minus dN1 by dt, that is the rate of change of number of primary particles N1 per volume, that will be equal to 8 pi dr N1 square. And this equation presumes that every collision is effective in removing two primary particles from the system if their centers approach to within the collision radius capital R. But in our approach here, we are concerned with total number of particles in the system, and each collision in effect will remove only one particle, because before collision there are two like particles, after collision there is one particle. So, in effect we have removed only one particle from the total number. So, we change our notation here a bit. Moving from the primary particles, we have now n, the total number of particles in the system, that is dN by dt. This should be minus dN by dt equal to 4 pi dr n square. Integration of this equation leads to 1 by n equal to 4 pi dr small t plus a constant. At time 0, the number of particles per cc is n0. So, that constant is 1 by n0. Substituting that, we get 1 by n minus 1 by n0 is equal to 4 pi drt. And this equation, this result has been checked against experiments, many experiments, including stearic acid smoke coagulation. So, there may be one way of checking it. You could plot 1 by n versus t, that should be a straight line with a constant slope of this 4 pi dr. Or the other way would be that you look at a time when the total number of particles changes, reduces from n0 to half that value. So, at t equal to t half, n will become equal to n0 by 2. This should read as n0 by 2. At t equal to 0, n is n0. At t equal to t half, n is n0 by 2. Correspondingly, the t half will come out to be equal to 1 by 4 pi dr n0. So, you could check at what time the initial total number of particles per cc reduces to half the original value n0 by 2. As for second order chemical reaction, we see that this T half is inversely proportional to the initial number of particles, total number of particles present n0. The diffusion coefficient here for the particles, this is not molecular diffusion coefficient, may be regarded as Brownian diffusion coefficient for that dimension of particles, is given by the equation given by Einstein, and that is kT by 6 pi eta A, where K is Boltzmann constant, T is absolute temperature, eta is the viscosity of the medium, the continuous phase or solvent whatever we have, and this small a is the radius of the particle. So, if you look at d estimated from here and then plotted for this stearic acid smoke coagulation as 1 by n versus t, you get a pretty good agreement between the prediction and the experiment. There is only one limitation for this diffusion coefficient relation. The particles that you are calculating diffusion coefficient for should be large compared to the mean free path of molecules. We could think of next the emulsions. Emulsions are made by subjecting large oil droplets to high shear and you split these into smaller daughter droplets. If you are thinking of oil being dispersed in water, you can think of water being vigorously mixed with a mechanical agitator and you add large oil drops to it, which when they enter water are subjected to turbulent shear, which will tend to break these droplets into smaller ones. Supposing that in the initial concentration we only look at the dispersed phase and the continuous phase. The dispersed phase is oil, continuous phase is water. Oil droplets subjected to turbulent shear conditions will break into smaller droplets. There is nothing to stabilize. So, you can think of this droplet being bombarded by turbulent eddies and then breaking into these ones. Intermediate picture could be maybe something like this, where the instability takes the droplets into separate droplets. But the reverse can also happen. When you have these daughter droplets or other droplets which are floating around, by the similar eddies movement, random chaotic movement, they may actually bump against each other. If you look at the reverse, it might actually be these droplets are coming closer together. This is oil, there is a water film in between. If these approach each other and squeeze out the water in between, they may actually coalesce, right. So, this part is the reversible part, reverse part. So, you might have shear breaking it into smaller droplets and random eddies bringing together these droplets and squeezing the film of continuous phase will cause the mergers or coalescences or coagulation. So, one of the simplest models for emulsion formation was based on this picture. So, I would like you to think about a few things here. The first is, if we have to write how the number of emulsion droplets, dispersed phase droplets will change with time, based on this mechanism, how would we formulate the equation? So, you are already saying that it is to be treated like a reaction. The forward reaction is breakage, the backward reaction is coalescence. And the coalescence is the backward reaction or the reverse reaction. Now, if you choose, say, the number of dispersed phase droplets as n, and you want to write n droplets per volume of the continuous phase, n droplets of dispersed phase per volume of continuous phase, how these are changing with time, you want to write dn by dt. How would we write this? Or on similar terms, minus dn by dt, how the number of droplets of dispersed phase per volume of continuous phase will change with time. We go by the reaction. The forward reaction is corresponding to breakage, and let us say we are looking at only the binary breakage or coalescence. If a droplet breaks, it breaks into two droplets. If droplets have to coalesce, two droplets combine together and form one droplet, that is the simplest picture we keep. Then for the breakage, we might say there is a breakage rate constant Kb, and for coalescence we may say a coalescence rate constant Kc. Now, in terms of Kb and Kc, how would we write this? Minus dn by dt. Kb into n, Kb into n minus Kc into n square.
Positive d no? This should be positive d.
Correct? Supposing that there is no coalescence, then is this correct? Should it be minus dn by dt or plus?
Because they are increasing.
Coalescence is leads to disappearance.
Right. So, you will write this as, if the breakage is there, only breakage is there, number of particles will increase. If there is coalescence, if there is only coalescence and no breakage, the number of particles will decrease. If the two are present together, we will have this sign. Correct. Then at t equal to 0, you may have the same n equal to n0, and therefore, we can integrate this and obtain the expression for the number of emulsion droplets changing with time. You can obtain an index of stability, half life, for the number of droplets to come down to n0 by 2 if you start with initial number n0. This is one way in which you can approach the emulsions, breakage and coalescence. There are certain two phase systems containing oil and water which are stabilized with the help of a surfactant and perhaps a co-surfactant, such that you move from the unstable region of dispersions to a thermodynamically stable dispersion, that is the microemulsions. So, we will not worry about that. Those have many applications. Next is foam. Foam or froth will have very little liquid separating the bubbles. So, in foam the bubbles are actually polyhedral if we roughly represent them by the gas pockets here and the liquid film here. Then as a result of gravitational drainage, the liquid drains from within the liquid films, bringing these faces closer together. If they are stabilized by anionic or cationic surfactants, there will be some electrostatic repulsion when these faces start seeing each other. But this is only an isolated bubble. In a polyhedral foam, you have large number of such bubbles in proximity, and these films have a certain interesting ways to combine with other bubbles. These gas pockets are for different bubbles. Two bubbles are sharing this liquid film. If you take the polyhedral foam bubble, then one of the approximations or idealizations could be regular pentagonal dodecahedra. What it means is each flat film is regarded as pentagonal of equal sides, regular, and each bubble has 12 such faces. So, the common foam that you see with large bubbles, they are polyhedral. If the bubbles are very small, they will be spherical. So, the foam is one which is polyhedral and spherical bubbles are in froth. Some people reserve the word froth if there are particles within the liquid, so that if you let a layer of froth vaporize, it will leave a thin film of solids at the bottom. That probably has to do with the froth flotation, which is a much older process compared to other applications of foam. Now, if we have this structural idealization that each polyhedral foam bubble is like a dodecahedron, each with 12 pentagonal faces, each face with the same length of side, you have one visualization. You take many such polyhedra together, dodecahedrons together. If they are all of same size and you put them together, there is one conceptual catch, that is, you are not able to fill space completely. If you take cubes, you can fill space completely because they will be exactly matching faces, leaving no gap. But in these dodecahedra, there are certain gaps which are not filled. They amount to about 3%. So, it is presumable that those voids are filled up with liquid, forming the films. Okay. Now, each face has those 3 sides. Those sides in real foam are not line segments, but they have certain thickness. They are called Plato borders. They have a cross section which is curvilinear. If you take a cross section, this is how Plato border will look. This is a part of one film, this is part of another film, this is a part of third film. So, if you call them F1, F2 and F3, 3 films are meeting together in this edge or the side, which is like a curvilinear pipe, all made of liquid, no sides, no surface, no wall. Then we have liquid here, and a little consideration here from the Laplace-Young equation will tell you that the pressure at the center and pressure in the film in the flat region, when compared with the pressure in the center of the bubble, will tell you something interesting about drainage. Think of this. Supposing you call this P1, this as P2 and this as P3. We want to know how these pressures are relative to each other, such that that analysis can tell us how liquid will flow within the Plato border. Now you can think of, let us say, first comparing P1 and P3. P1 minus P3 will be given by Laplacian equation as 2 gamma by R between 1 and 3. But what is the radius of curvature for this flat region? Radius of curvature is the radius of that sphere of which this will be the surface. For a sphere to have flat surface, the radius will have to be infinity, isn't it? So that means this is infinity. If this is infinity, 2 gamma, a finite quantity by infinity, will be 0, which means P1 is equal to P3. If similarly you consider P1 and P2, P1 minus P2, it will be 2 gamma by R12. Radius of curvature for this surface is some finite radius R12. So this is a positive quantity, which means P1 is greater than P2. But P1 is equal to P3, P2 is equal to P1. So P2 is greater than P3, which means the pressure here is higher than the pressure here, and the liquid will flow from a higher pressure region to lower pressure region, which means liquid goes from the center of the Plato border right. You have P1 equal to P3, P1 greater than P2, so P3 is greater than P2, which means the liquid flows from P3 to P2, reverse of what I am saying, right, which means the liquid is flowing from the flat region of the film towards the center of Plato borders. Okay. All these sides are connected, all the Plato borders are connected, they form a network. So everywhere the liquid is flowing from the center of the film towards the center of the Plato border, and through the Plato border network the liquid is flowing downward, all right, which means this should be possible to visualize. If you were to take a height of foam of some surfactant solution, aqueous solution, and in the same solution you dissolve a dye for visualization like a red dye, and you put the drop at the top, what would you get to see? The color of this drop will let you visualize how that dye solution is trickling down. If this theory is correct, it shows that the liquid film must thin and liquid should be dumped into the Plato border. If you add such a drop of liquid at the top, even if it were to be placed at the center of the Plato border, it will not be able to go into the flat region of the films. It will be drained off through the network of Plato borders. So you will be able to see actually this red drop travelling down through the network of Plato borders. The films will remain colorless. You might object to this by saying that the films are very thin, so even if they are colored, you might not be able to see. But actually, even if you make that observation carefully, you would see that the flow is through the plato borders, whereas the center of the film, which is at higher pressure compared to center of plato border, will not accept liquid. Okay? So, the drainage occurs through network of plato borders. But the film drainage does occur, and these films thin down over a period of time, and they may become so thin that any extraneous vibration may be able to break this foam film. And you know, in actual foam, in practice, we have all bubbles not of same size, they are of different sizes. So, the smaller bubbles will have a higher pressure, excess pressure. So, the gas will diffuse from smaller bubbles into larger bubbles, and there is another way in which the foam breakdown occurs without any rupture of films. So, these are the two mechanisms. We will stop here for today.